In this lesson, we will continue our review of calculus. This lesson assumes that you already reviewed derivatives. We will now review integrals. Recall that if y is equal to x squared, then the derivative of y with respect to x, which we can write as y prime, or as dy over dx, or as d of x squared over dx, is equal to 2x. When we say antiderivative of function f, we mean a function whose derivative is f. So, since we know that the derivative of x squared is 2x, which of these two functions is an antiderivative of the other? We can say that x squared is the function whose derivative is 2x, so x squared is an antiderivative of 2x. But we also know that if y is equal to x squared plus 3, its derivative is also 2x. So we can also say that x squared plus 3 is an antiderivative of 2x. In general, we can add any constant to x squared, and the resulting function would be an antiderivative of 2x. The term indefinite integral refers to any one of the antiderivatives of a function. In other words, the indefinite integral of 2x is x squared plus c, where c is an arbitrary constant. We call c the integration constant or constant of integration. When we say arbitrary, we mean it could be any constant. Don't stress over the distinction between antiderivative and indefinite integral. For practical purposes, you can use them interchangeably. A more straightforward way of saying that x squared plus c is the indefinite integral of 2x is to write something like this. The process of determining the antiderivative is called integration. The symbol, which looks like an elongated S, is the symbol for integration. We read this expression as the indefinite integral of the function 2x with respect to variable x is x squared plus c. To save time, we can just read the equation as integral of 2x dx equals x squared plus c. Here we can say that the function 2x is the integrand, and we refer to x as the variable of integration. As mentioned earlier, c is an arbitrary constant. It's quite common in textbooks to generically represent the integrand by lowercase f and the antiderivative as uppercase f. So in general, we can say that the indefinite integral of small f with respect to x is big F plus c. Since the derivative of big F is little f, we can also say that the integral of the derivative of any function is equal to the function itself plus an arbitrary constant. In other words, taking the indefinite integral essentially means reversing the differentiation, but we add an arbitrary constant. Suppose we take the indefinite integral of a function shown here as little f of x. In general, we get another function of x, represented here by big F of x, plus an arbitrary constant c. The definite integral of the function between two values of x is obtained by evaluating the function big F at the two values of x, then taking the difference. Let's say we want the definite integral from x equals a to x equals b. We specify a and b next to the integration symbol as shown here. We refer to a and b as the limits of integration. We say that a is the lower limit and b is the upper limit. To evaluate the definite integral, we plug in the values of a and b in the expression for big F. Then subtract the result of plugging in the lower limit from the result of plugging in the upper limit. Let's illustrate with a simple example. We've seen that the indefinite integral of 2x with respect to x is x squared plus c. So, if we want the definite integral from x equals 2 to x equals 3, we substitute the upper limit, 3, for x, And do likewise for the lower limit too. Then take the difference between the two results. 3 squared minus 2 squared is 9 minus 4, which is equal to 5. When reading an expression that involves an integral, we don't really need to say whether it's a definite or indefinite integral. That's because if we specify limits, we know we're dealing with a definite integral. But if we don't specify limits, then we know we're talking about an indefinite integral. So we can just read this as the integral of f of x with respect to x, or more simply as the integral of f of x dx. And we just read this as the integral of f of x dx from x equals a to x equals b. How do we interpret the value of a definite integral? Consider the integral of function f with respect to x from x equals a to x equals b. The value of this definite integral is the area under the curve from x equals a to x equals b if we plot function f versus x. By area under the curve, we mean the area between the curve and the x-axis. The area is positive if the curve is above the x-axis, and the area is negative if the curve is below the x-axis. Consider this plot of function f versus x. Note that for the area shaded in yellow, the curve is above the x-axis. So the definite integral from this x value to this x value is positive. For the area shaded in red, the curve is below the x-axis. So the definite integral from this x value to this x value is negative. There are some integrals you need to know by heart. Suppose y is equal to a, where a is a constant. Then an antiderivative of the function is a times x. Here's an example. What is the integral of 5 dx? Here, the integrand is a constant, which is 5. So the indefinite integral is 5x, plus an arbitrary constant c. To verify, we take the derivative of 5x plus c. It's easy to see that the derivative of 5x plus c is 5. Try this one. What's the integral of dz? Note that the variable of integration here is z, not x. So the indefinite integral will be a function of z. Since dz is equal to 1 times dz, it's easy to see that the indefinite integral is just 1 times z, or just z, plus the integration constant c. Suppose y is equal to x raised to some power n. Then the antiderivative of this function is x to the power n plus 1 divided by n plus 1. Note that this formula is valid as long as n is not equal to negative 1. Why? Well, if n is negative 1, then n plus 1 will be equal to 0, and we would get a 0 denominator, which would make this expression undefined. Remember that division by 0 is undefined. Let's look at an example. What is the integral of x squared dx? Here, n is 2. So the numerator x to the n plus 1 is x to the 2 plus 1, which is x cubed. For the denominator, n plus 1 is 2 plus 1, or 3. Therefore, the integral of x squared dx is x cubed over 3 plus c. You should be able to easily verify that the derivative of x cubed over 3 plus c is in fact x squared. We know that the derivative of ln of x is 1 over x, or x raised to the negative 1. Therefore, what would be an antiderivative for y equals x to the negative 1? That would be the natural logarithm of x. What is the integral of du over u? We can write du over u as 1 over u times du, or as u to the negative 1 times du. Therefore, the indefinite integral is equal to natural log of u plus c. Note that since our integration variable is u, the indefinite integral should be a function of u. We know that the derivative of e to the x with respect to x is also e to the x. Therefore, what is the integral of e to the t dt? That would be e to the t plus c. We also know that the derivative of sine x with respect to x is cosine of x. Therefore, what is the integral of cosine z dz? The indefinite integral would be sine of z plus an arbitrary constant. How about the integral of sine u du? Well, we know that the derivative of negative cosine x is the sine of x. This means that the integral of sine u du is the negative cosine of u plus c. Here's a couple of identities that you should know by heart so that you can integrate more complicated functions. The integral of a sum is equal to the sum of integrals. Here's an example. Here, our integrand is a sum of two functions, sine of x and 1 over x. We can write this integral as a sum of two integrals. The integral of sine x, which is negative cosine x, plus an arbitrary constant, and the integral of 1 over x, which is the natural log of x plus an arbitrary constant. We can combine the integration constants for both integrals. As usual, let's call it c. So the integral is negative cosine of x plus natural log of x plus c. Another important identity has to do with multiplication of a function by a constant. The integral of a constant times a function is equal to the constant times the integral of the function. Here's an example. What is the integral of 6 times e to the x with respect to x? Here we see that our integrand is a constant times a function. The constant is 6 and the function is e to the x. So we can factor out the 6, and the simpler integral that we need to evaluate is e to the x with respect to x. We know this to be e to the x plus an arbitrary constant. 6 times an arbitrary constant is just another arbitrary constant, which we can represent by capital C. So our final answer is 6 times e to the x plus c. Variable substitution is a very useful technique for evaluating integrals. Let's look at a simple example. Consider the integral of sine kx with respect to x, where k is a constant. We know that the integral of sine x is negative cosine x plus c. But the problem is that the argument for our sine function here is k times x, not x. To make the integral look like the one that we know, we can make a substitution. Let's define the variable u as k times x. Then sine of kx will now be sine of u. But now we also want to change our variable integration from x to u. To do this, we need to relate dx and du. This is easy to do because the derivative of u with respect to x is the derivative of kx with respect to x, and it's equal to k. We can rearrange this equation to solve for dx in terms of du. We get dx equals du over k. So now we substitute sine of u for sine of kx and substitute du over k for dx. 1 over k is a constant, so we can factor it out of the integral. So now we have 1 over k times the integral of sine u du. The integral of sine u du is negative cosine of u plus an arbitrary constant, which we are representing here by lowercase c. Multiplying by 1 over k and substituting kx for u gives us negative 1 over k times cosine of kx plus lowercase c over k. Since lowercase c over k is just another constant, we just replace it by another letter. Here, as usual, we use uppercase c. Recall that the derivative of a product of two functions is equal to the first function times the derivative of the second plus the second function times the derivative of the first. If we call our two functions u and v, then the derivative of u times v with respect to x is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. If we multiply this expression by dx, dx cancels out and we get this expression. We read it as differential of u times v is equal to u times the differential of v plus v times the differential of u. Or we can just say d of u times v is equal to u dv plus v du. We can rearrange this equation so that only u dv is on the left-hand side. If we do, the right-hand side will be d of u times v minus v du. If we integrate both sides of the equation, we get this expression. On the left-hand side, we have the integral of u dv, and on the right-hand side, we have u times v, which is what we get when we integrate d of u times v, minus the integral of v du. You can use this identity if you can imagine the integrand as a product of two functions u and f, so that if you let f dx equal to dv, it would be easy to find the integrals of f dx and v du. Note that the integral of f dx is v. Let's take a look at an example. Let's use integration by parts to integrate x times e to the x dx. Recall that to integrate by parts, the formula is integral of u dv is equal to u times v minus the integral of v du. Here, we can let u be equal to x and let dv be equal to e to the x dx. The motivation for doing this is that it is easy to get the integral of e to the x dx. It's just e to the x. Therefore, v is equal to e to the x. So now we can write the integral of x times e to the x as, here u times v is x times e to the x. Now the integral of v du is just the integral of e to the x dx. Note that v is e to the x. And du is equal to dx since u is equal to x. So our integral is equal to x times e to the x minus integral of e to the x dx. This simplifies to x times e to the x minus e to the x plus an arbitrary constant c.